Welcome to Samveda e-learning program. Today for 10th standard we are discussing about the topic electricity. As you can see, this topic electricity is divided into 5 sessions, and the first session that we are engaging today is called as basic concepts in electricity. Now which are the next sessions that you are going to see? As you can see, the second session is Ohm's law, third session is the factors on which the resistance of a conductor depends, and fourth session is resistors in series and parallel, and the fifth session is heating effect of electric current. Children, in today's world we know how much dependent we are on electricity. We get many of our works done at home by using electricity. It makes our work very simple and easy. And in industries we use electricity to manufacture things. And in today's globalized world, we use electricity for communication through mobile and internet devices. Overall, it is very difficult to imagine the world without electricity. To understand it, come let us watch this activity. Children, you just watched this activity. So what is the reason for the hairs to get attracted? Yes, it is the charges which are present in the balloon that attracts the hairs. So how is it happening? Yes, this is what we call as static electricity. I am sure all of you have done this activity. By making use of comb, if we comb our hair and bring that comb near to the paper, what will happen? Yes, you all know that the paper pieces get attracted with the comb. So what is the reason here? In the balloon activity, the balloon was attracting the hair. Here the paper pieces are getting attracted to the comb. So what is the reason? Yes, you are right. The reason is it is static electricity, or the charges which are present at the ends of the comb, and it is attracting the negative charges on the piece of paper. One thing you have to remember here is we call it as static. That means these charges are not moving. They only get attracted to each other. This is why it is called static electricity or static charges. Children, if you can see, what are the charges present here? Yes, you are right. These two are positive charges. And what is happening between them? As you can see, they are moving away from each other. When you come to these charges, here one is positive and the other one is negative charge. What is happening? They are getting attracted to each other. So we call these two charges which are having the same type of charge as like charges. And if the two charges, one is positive and the other is negative, then it is called unlike charges. So what will happen when the charges are same or when the charges are like charges? Yes, they repel, and when the charges are unlike, they attract. I think all of you have seen in the magnets also that when you bring a north pole to north pole nearer to each other, then it will repel, or south pole to south pole, then also it will repel. In the same way, I will ask you a question here. What will happen if you put two minus charges near to each other? Yes, I am sure you are answering it correctly, that again they will repel. So like charges, they repel each other, and unlike charges, they attract each other. Children, now to understand more about charges, come let us go into this activity where we will verify how the charges behave in an electric field.
Children, now let's see what happens to a unit charge in an electric field. As you can see, one unit positive and negative charge you can observe at the bottom here. Let us bring in a one positive charge inside the electric field. This red colored one is the positive charge. See what is happening to the other charges in the field. As soon as we bring the positive charge, they are moving away. That means now let us see for the negative charge. As the negative charge is brought inside, all the other charges, positive charges, are getting attracted towards the negative charge. So As you can see, when the unit negative charge is moving in the electric field, all the positive charges are attracted towards it. You can observe the direction. Now, when the positive charge is brought in the same direction, you can see the other positive charges are moving away.
Children, you have just seen how the charges behave in an electric field. Now, I want to ask you this question. For the flow of electric charges in a circuit or in this torch, how should we connect the two cells? How should we connect? Either should we connect in this option or should we connect in this manner? Yes, children, you are right. We should connect in this manner. Now, what is the reason here? Yes, again, as you just saw, that unlike charges attract each other. So, here as you can see, the positive charge and the negative charge, they attract each other, so the charges flow in the circuit. Here we have both the charges as negative charges, so they will repel, the charges will not flow. Now here I want you to have a distinction. Earlier we were talking about static electricity, charges were not moving. Now we are talking about moving charges. So this is what we do in electricity. Now, how do we measure electric charge? The unit that we use for measuring electric charge is coulomb. Now, you know that charge on one electron is 1.6 into 10 to the power of minus 19 coulomb, which is a negative charge for an electron. Now, the question is, how many electrons will make the charge equal to 1 coulomb? How can we calculate it? Come, let us find it out. Here we are making use of this equation, that number of electrons into charge on one electron is equal to 1 coulomb. That means how many electrons should we add to make the charge equal to 1 coulomb? We know that charge on one electron is 1.6 into 10 to the power of minus 19 coulomb. Now, if we put the value 1.6 10 to the power of minus 19 coulomb in place of charge on one electron, then we can calculate the number of electrons which will make the charge equal to 1 coulomb. As you can see, if we transpose it, it will go to the denominator and we will get the value that the number of electrons is equal to 0.6 into 10 to the power of 19. Now, if we adjust it to the decimal place, then we can write the same thing as 6 into 10 to the power of 18 electrons. So now we know what is the value of 1 coulomb. That means it is the charge collectively present in 6 into 10 to the power of 18 electrons. So whenever the charges are moving in a conductor, we call it as electric current. Now here as you can see, there are charges, a representation of charges and a conductor. If we take any one particular cross section of area, either this or this, whichever cross section of area, if we calculate the total number of charges that are crossing that area of cross section, then that is the value of electric current passing through this conductor. Just like if in a pipe the amount of water that is flowing from a particular point, we call it as, in the same way we are calculating the number of charges that is passing a cross sectional area in this conductor with respect to a specific time. So here that is what we call as electric current. Electric current is the amount of charges flowing through a particular area of cross section in unit time. Now as you can see, if the total charge that has passed through the area of cross section is q and the time that we have considered is t, then we can calculate the electric current as the number of electrons flowing divided by time. Here we can calculate the electric current as the total charge in unit time. As you can see, I is equal to q by t. Q is the total amount of charge that is flowing through a particular area of a cross section. Now we know what is electric current. Now how do we measure electric current? Yes, you are right. Here you are seeing an instrument called as ammeter which measures the electric current. That means it measures the charge which is passing through the conductor in unit time, and the SI unit of electric current is ampere. Now, what is called as 1 ampere? As you saw, that charge by time is electric current. If the electric current is 1 ampere, then the charge should be 1 coulomb Q and time should be 1 second. That is when we call the electric current is equal to 1 ampere. Children, here we have seen the ammeter. Now you can see it is connected in this manner in the electric circuit. Now why is it that is connected in this manner in an electric circuit? It is connected with the battery, or what we call it as series connection. Now you may know that at our homes we have a meter to measure the amount of water we use, right? So the water supply that enters our homes is at the entry point, the meter is fitted, so that entire water that is the home is consuming is being measured through this meter. In the same way, we have to put the ammeter with the battery in series, so that the entire electric current flows through the ammeter to measure the amount of electric current. Now we know what is electric current and we know its equation. Shall we solve a numerical problem? Yes. A current of 0.5 ampere is drawn by a filament of an electric bulb in 10 minutes. Find the amount of electric charge that flows through the circuit. So as you can see, the electric current is 0.5 ampere I and the time is 10 minutes. Now if we convert the minutes into seconds, 1 minute is 60 seconds, so we are getting 600 seconds. I we have known and T we know here. Now we will calculate Q. As we know the equation I is equal to Q by T, if we cross multiply it, Q is equal to I into T is the equation we get, because we are finding the amount of charge. Is equal to I we have substituted 0.5 amperes and 600 seconds. So by multiplying we get 300 coulomb. So that is the amount of electric charge. Children, now you have seen how to calculate the electric charge. My question now is, do we need to put the electrical components in a proper manner so that the current flows in it? Is there any proper way? To find it out, come let us see that activity and come back to this concept.
Children, now let us see here a simple electric circuit. As you can see here, the electric cell is connected through wires and a switch and a bulb. Here this switch is open, that means electric current is not flowing, and it is the bulb. So the terminals of the cell, we have the positive terminal and the negative terminal. So right now the electric current is not flowing, and we know since the switch is open. Here you can see a representation of electrons inside the wire. So we need to observe what happens as soon as the switch is closed. Children, can you answer what may happen here? Yes, you are right. As soon as we close the switch, the whole path for the electric current is closed. That means as soon as we close the switch, the electric current starts flowing. As you can observe, the charge or the flow of charges, that is the flow of electrons, it is from minus terminal of the cell to the plus terminal of the cell through the wire and through the bulb, and also you can see the bulb is glowing. That means the circuit is closed and the charges are moving.
You have just seen how that electric current is flowing only when the circuit is closed, right? So, a continuous and closed path for electric current is called as a closed circuit. We need to arrange the components in a specific manner for the electric current to flow inside the circuit. Children, now we have seen how the charges move when the circuit is closed. My question is, does electric current have a direction? Yes, you are right. You have seen it already in the activity that charges are moving from one point to the other. Now, earlier in the beginning, when the studies were going on regarding charges, they did not know the existence of electrons. So, they did not know about the proper movement of electric charges. Then they believed that the electric current is a flow of positive charges. That is what we call as conventional direction of electric current. As you can see, we have shown here the red mark shows the flow of positive charges, which is the conventional direction of electric current, and the green arrow shows us the direction of actual current, that is the flow of electrons, which is from minus to plus. Now, why do electrons move from minus to plus? Yes, you know the answer, that they are attracted to positive charges. So, you need to remember the direction. Conventionally we say the direction of electric current as plus to minus, and actually the electron flow happens from minus to plus, but we consider the direction of electric current to be from plus to minus. It is a convention. You have seen some of the examples of electric circuit today. Now, there may be components which are too complex to draw on a paper. In such a situation, how can we simplify this problem? Yes, this is what we call as the concept of circuit symbol. If you can see, these are the electrical components. What is this? It is a cell. What is this? This is a resistor. This is an electric bulb. And if you can look here, there is a proper symbol for each electric component. This is the symbol of cell. This is the symbol of resistor. So, what will happen if we use these symbols? Yes, you are right. We can write it on a paper, the electric circuits in a simple manner, so that everyone comprehends what this electric component is, no matter how the shape changes from one place to other. Here, if you can look, you will see that what all the symbols we have for different type of electric components. Electric cell, we have this symbol. A battery, what is the difference between battery and a cell? In battery we will be having more than one electric cells. So, this is the switch that we are seeing, or plug key. In the same way, you can see various types of electric symbols for electric components. Here also you can see that this is two wires which are crossing without joining, and the symbol of ammeter and voltmeter. Children, now let us have some questions. A continuous and closed path of an electric circuit is dash. Which is the right answer out of these three, whether electric connection, electric distribution, or electric circuit? Yes, I am sure you are answering it right. So, it is electric circuit, which is the closed path of an electric current. Second question, 1 coulomb is equivalent to the charge contained in these many number of electrons. So, here you can see three different types of numbers of electrons we have given. Which is the right number of electrons to make it equal to 1 coulomb of charge? Yes, you are right. I think this is 6 into 10 to the power of 18 electrons make the charge equal to 1 coulomb. Here, if you could see, there are two beakers we have taken and they are connected with a pipe. My question to you is, this is the first container, this is the second container. The water, will it flow from the first to second or second container to the first container? Yes, you are absolutely right. You know that from the second container the water will flow to the first container. Now what made you to answer in this way? Yes, you noticed that here there is more amount of water and here this is less amount of water. So here high pressure is there, here low pressure is there. That is why it moves from a high pressure region to a low pressure region, right? So you should focus on the difference of pressure present here. That means whenever there is a difference of pressure, there is a motion there, motion of particles is there. In the same way, the movement of charges happens in an electric circuit, because a battery has a difference of charges at its endpoints. One is high pressure, another one is low pressure. So it creates this sort of difference of electrical charges by making use of these batteries or these cells. So children, here the work is being done by this difference in pressure. In the same way, the work that is being done for the movement of charges is by this cell because of the difference in pressure of charges at its two ends. So we know that for any object to move, we need to do some work on it to move from one place to other. So in electric circuits, who is doing the work? Yes, these type of electric sources, cells, they are doing the work. What do they have to do that work? Yes, they have a difference of pressure of charges at their ends, which makes them to do that work. So this difference is what we call as the potential difference or the electric potential difference. Whenever a difference in electric potential is provided to a conductor, then the charges in the conductor, they start moving. Unless we give this sort of difference in pressure of electric charges, the charges in the conductor, they don't move, because in a conductor there are many free electrons already. If you take a wire, there are many free electrons. But why do they not move in one particular direction? Yes, we should do some work on it, only then those free electrons will be moving in a one specific manner. So that work is being done by the cells by providing the potential difference, which is the difference in charges or difference in pressure of electrical charges at its ends. So we can define that the potential difference or electric potential difference between 2 points in an electric circuit carrying some current is the work done to move a unit charge from one point to the other. How can we put it in a mathematical equation? Yes, as you can see, potential difference is the work done per unit charge. That means the amount of charges that we can move from one point to the other by applying or by doing this amount of work. So V is equal to W by Q. V is the potential difference, W is the work done, and by making this work done, we are moving these many number of charges or these amount of charges Q. Now when do we call the potential difference as 1 volt? Yes, when we do the work 1 joule and 1 coulomb of charges are moving, then we call the potential difference as 1 volt, because we know that when we give this difference, we are doing the work, and when we are doing the work, the amount of charges are moving from one point to the other. The SI unit of electric potential difference is volt, named after the scientist Alessandro Volta, who is an Italian physicist. Now children, earlier we saw how to measure the electric current in an electric circuit. Now here, how can we measure the potential difference? Yes, you already saw that in the activity we use the instrument called as voltmeter. Now the potential difference is measured by using voltmeter. And how do we connect the voltmeter in a circuit? It is in a parallel connection, so that we are finding the potential difference only at the two edges. In this circuit where we used electric cell, the potential difference is being generated by the chemical action inside the cell. Because of it, the charges in the conductor are set in motion and an electric current is produced. In order to keep the current flowing inside the conductor, the cell should keep on expending its chemical energy to make the charges keep in moving, or to make the electric current keep on moving. Children, here let us solve a problem on potential difference. As you can see, how much work is done in moving a charge of 2 coulomb. So, that is the value of Q, that is 2 coulomb amount of charge, and the potential difference across 2 points having a potential difference of 12 volt, that is V. V is 12 volt. So, now the amount of charge Q that flows between 2 points at potential difference V is equal to 12 volt is 2 coulomb. Thus, we can calculate the amount of work done by using W is equal to V into Q, because V is equal to W by Q. By cross multiplying we will get this. So, 12 volt into 2 coulomb, that is 24 joule. That is the amount of work done to move 2 coulomb of charge in a potential difference of 12 volt. Children, let us have a small quiz here. Can you identify which is this electric symbol? What does it symbolize? I think you are giving a correct answer. Yes, it is an open switch. That means it is an open circuit, or where the current is not flowing. This is an open switch. Next question, if you can see here, identify this electric symbol. Yes, what is that electric symbol? Of course, you know those are wires. So, what is the answer for this? Yes, I think you are giving a right answer. They are a wire that is having a joint. That means the wires are connected. They are not crossing over without joining. Children, today whatever you have learnt, what you need to do is try to solve it. Here is the first question. How much work is done in moving a charge of 3 coulomb across 2 points having a potential difference of 13 volt? Please write it down. Define electric potential and potential difference. I think you have noted down the homework. Don't miss out on this. Solve it and solve as many questions in the exercise. Yes, dear children, today we have seen some of the basic concepts in electricity. That is the first subunit, and the next 4 subunits we are going to learn in the subsequent classes. So, thank you all.